I'm going to talk about life from inside out. And now the question is, what does that mean? And I thought to illustrate that with my background on what I'm actually doing mostly every day. And that's something I had to do with this kind of little video I made over here. Now, when we look out there, we discover and see a lot of planets that are just like that, quite rather no oceans, no forests, like Mars or Mercury. And sometimes we hope to find planets that are kind of blue, have oceans, look like Earth, have continents, have maybe oxygen atmospheres. And we wonder why they are different, how they actually, where they can be formed. And now, there's many ways of addressing the question. And my approach is to look at what's happening below our feet. Because we're standing on this huge ball, which is the biggest mass, actually, of a planet. And we live just on a shallow surface. Now, this big ball has huge impact on what's happening on the surface. It impacts volcanism, plate tectonics, magnetic field generation, origin of different food networks. And only when we really understand what's happening inside of planets and the interaction with the surface, only then are we really capable of understanding why a planet is truly Earth-like. And that's the approach that I'm taking when I start to study these kind of questions. And to the outline of my talk, I want to just quickly, I know everybody's from different fields, so if I'm boring you with too much general things, please let me know. But I want to start in the beginning with just refreshing our memories for those who are not in that field, what's really happening inside planets, in the interior of planets. And then I want to focus on a few aspects, what people speculate or talk about connections between deep interior and life. What are connections? I'm going to focus on the question whether magnetic fields are important or not, or on plate tectonics and volcanism, a field I was also working actually mostly on. And then I just would like to actually give you a few snapshots, give you a flavor of specific questions. And here I'm going to focus on two things that I'm working on. One thing is plate tectonics and its evolution on Earth and across the galaxy, very Star Trekian but very important, and on the dynamic rise of life, showing you how the rise of life, the origin of life, and the evolution of life on the Earth and maybe other planets was controlled by interior dynamic processes. And then quickly just resume the main message. Now, you see there's something like shimmering and dark gray down there. This is intentionally there. I promise to do much more of my abstract, but I don't want to really kill you with too much information. So there's some extras about atmospheric oxygen and interior correlations, how oxygen actually was formed, and also all the details of the models and the thermodynamics. So for those who have much more questions later on, I'm very happy to answer those. However, I'm going to now focus on the major beginning part and understanding what really happens inside planets. Now, when we look at the Earth and take a deep look below our feet, which is quite difficult because you can't really look through it, and our indirect measurements and tools to understand these kind of processes are also quite limited. However, what we see for the Earth is it is differentiated in a rocky mantle and a metallic core. So it's separated in two big layers. The mantle, in this case, is based on diverse minerals, silicates, oxides. And what's really important, we talk about fluid dynamics, but the Earth nowadays is mostly solid. So there's small bunches of melt in the upper mantle, maybe in the lower mantle, but generally this whole planet, the mantle piece, is mostly solid. What's really important to always memorize, radiogenic heat sources are something natural, and the Earth is full of them. So especially the Earth's mantle is full of radiogenic heat sources which decay in time, but also heat up the planetary interior. Now, the core itself consists of, in the Earth, mostly of iron and some impurities. It could be sulfur, oxygen, silicon, and many other things. And it's partially liquid. And I always love to ask this question. I did actually already once in the beginning of a class. The liquid part is the outer part of the core. And I always like to ask the question, why is the outer part liquid? Because, if we go closer to the core, it gets hotter. So why is the outer part liquid, although it's hotter in the center where we have actually solid material? Yes?
Less pressure.
Exactly. So pressure effects are really important. But that's something that we think it's really trivial, but unfortunately when we look at many planets, we forget about pressure effects. And that's one of the major problems why we actually have problems with understanding planets. Now, this was Earth. But let's have a look into the diversity of rocky planets. And with rocky, I call here a large class that is simply not gases. What we see here is this little glimpse into the solar system. We see Mars, we see Mercury, and then some Jovian satellites, moons of Jupiter. What we notice is that they're very different. The Earth is just one of many flavors. We have different compositions, different structures. Example, looking at Mars, it's half the size of the Earth, has a much smaller core. We don't really know much about the core yet. That will change in the next few years, most likely. We know that Mars has much more iron in the mantle than Earth has. But generally, there's a huge diversity out there, but we don't really have much detailed insight into those objects. It's quite limited. What we see here as well is what's really important. Some of these objects are differentiated, which means again we have a core and a differentiated rocky mantle. Some are not, like Callisto, which you see here, which we believe is not differentiated. So rock and metal are mixed with each other everywhere. And that's a really important process, the differentiation process. We believe nowadays that planets of the size of the Earth have no problems doing that, differentiating. However, we know that very small objects, and maybe even very large rocky objects have problems differentiating. And another thing which we notice is some of them have magnetic fields, and some don't. Now, the questions are, they're very different, but why are they so different? And one way of addressing this whole question is starting understanding how heat flows through planets. Now, the planet you stand on is a big, just huge bulk of energy. And there's cooling happening. We have a surface, we're in the vastness of space, and we're radiating heat away. Now, this cooling mechanism of a planet, and I'm going to explain these images in detail, is controlled by the mantle mostly, and by the surface conditions. The surface conditions in that case, it's much more, but in general, will be the surface temperature and the tectonic mode. And I'll describe in a few minutes what I mean exactly with the tectonic mode. Now, if we look here, the picture I'm showing on the left side, your left side, there we go, is a model that we've been doing for the Earth. M is Earth mass 1. The bigger guy over there is a 10 Earth mass planet, which has the same structure. The black thing you see here is the core. This is the core, and this is the mantle of the planet. It's a cut for it. It's a spherical 2D model where we model the heat processes in the planet. Now what we see as an example, what we know from the Earth is we have vigorous convection inside of the Earth's mantle. And this vigorous convection, what I show here is the velocity profile. So you see the speed of convection, and they go actually quite through the whole mantle. They start, we have some parts, we have here convective cells which go down, and in this case we don't have anything rising because of the boundary conditions, but in general we have convection in the whole mantle. Now the interesting thing is there are possibilities, I'm not saying that happens, but I said there are possibilities if we include a lot of pressure effects, and if you go to very large planets, that for certain configurations we might have problems with convection at very high pressures. That is much more tricky and complex because we have to understand planets evolving with time. But what I want to show here is heat transport in a planet will strongly depend on the planet mass, composition, structure, and many things we can't constrain. And if we look out to different planets, the heat transport in the planet might be different than what we know for the Earth, where convection, most likely full mantle convection, is cooling the planet. And for some certain planets, which maybe for very large planets, or for actually very small planetary objects, we might not really have convection and more conduction as a heat transport mechanism. Now, the important thing is, why does this cooling matter? Yes?
Sorry, can I ask a
Yeah, sure.
question? Is it obvious that planets will have, I'm totally ignorant, so Is it obvious that planets would have very different or very similar elemental composition to the Earth?
Oh, no, absolutely not, unfortunately. So planets can be very different in their composition. I mean, that's what we see already in our solar system. You know, if you look at Mars, look at the Earth, there's a different mineralogical composition in the mantle, different amounts of iron as an example, different amounts of oxygen, which, you know, allow to keep maybe more iron, more magnesium. And if you think about, you know, alien worlds out there, different stars, they might be very, very different from the Earth. And we're actually going to talk about that in about 15 minutes, where we're going to look how different planets can be alien and what it means, for example, plate tectonics. But it's a very, very important point. We are starting from the Earth. We should not use ourselves as an example for the whole galaxy or the universe. We're just one of these flavors. But so going back to the whole thing, so I mentioned that convection is important for heat transport in planets. And there's two end members for the so-called tectonic mode, which define more or less how the boundary condition on the surface we stand on interacts with convection. It's a bit more complex, but let's keep it their way. So we have in that case a stagnant lid and plate tectonics convection. Stagnant lid means simply we have a stagnant lid on top. There's a thick lid on top, which is not part of the convective movement in the planet. And we have plate tectonics, like we have on Earth, where, and that's I'm going to try and illustrate in this image over here, actually video, made by my colleague Christian Hüttig from the German Aerospace Center, where if we have plate tectonics, the upper part, the most upper part of the planet, of the lithosphere and the crust, are participating in this convective movement. So they're also being recycled. That's the whole deal. Now, the interesting thing is plate tectonics leads, case here of C for Earth, to continental drift. And what I want to emphasize is, although maybe for us it seems very natural to understand and believe, you know, there's plate tectonics, it's a new concept in a scientific term. People started thinking about that in the early 20th century, and they were debating it heavily for 50 years. In the late 50s and 60s, some universities were like saying, you can't talk about plate tectonics, this is absolutely ridiculous. And so it's a new thing we actually talk about. It's a new field of research. What's also interesting is there is no strong evidence on other planets than the Earth today. So we know there's plate tectonics in the Earth today. We don't see it nowadays, or there's at least no strong evidence nowadays on Mars or on other planets, which makes many people think, oh, that must be special. Because we, as my colleague in an article over there would mention, many people say, there's plate tectonics, there's life on the Earth, ergo, they must be correlated. Because on other planets, there's no life and no plate tectonics. But we're going to talk about that in a few minutes. Now, the interesting thing is on Earth, volcanism is often connected to plate tectonics. That does not mean that there's no volcanism without plate tectonics. It just means on the Earth, we have this tectonic mode, which is plate tectonics, and it often leads to volcanism. However, if we look in our solar system, we have Olympus Mons on Mars, gigantic volcano. Mars is full of volcanoes. We see the Venusian surface, which has been completely changed in the last few 100 million years. We see Io, Jovian Moon, and we see these planets are very, very geologically volcanically active, even nowadays, like in the case with Io. So plate tectonics is on the Earth associated often with volcanism, leads to volcanism. However, there is volcanism also without plate tectonics. That's important.
On Earth as well?
On Earth as well, yes. On Earth as well. Just think of Hawaii as an example. But that's a bit complicated because we're in the system of plate tectonics, so that's hard to say, but it can easily happen on the Earth as well. The important thing about volcanism, of course, very trivially, I think it's being pronounced Eyjafjallajökull. I was told that's how it's being pronounced. Was a few years ago, 4 years ago, and of course, we release a lot of volatiles and melt and heat. And as important thing is that when do we get melt? Now, this is an interesting subject, which seems very simple, but it's not so trivial actually. So we're getting melt. And this is a figure show over here. Imagine this is we're standing here on the surface. This is the interior going inside, and we have some temperature profile in green here. This is the temperature, so it's increasing when we go inside, and then it's increasing again, but a bit less deeply. And we have a so-called solidus, which is just more or less the melting temperature. It's where melt starts. So in some zone, we'll be hotter than the melting temperature, and we're going to produce melt. And in some cases, this melt can get out to the surface. But what's important is production of melt doesn't immediately lead to volcanism. That's very important. It depends on how deep you are. You can imagine sometimes if you're too deep, no matter if you have melt, you can't get that stuff out. And that's something to bear always in mind. Another thing is, it depends, of course, where we get melt. Now, the melting temperature is something, and here I'm showing how the melting temperature in Kelvin changes for magnesium perovskite with pressure, and up to 1,100 gigapascal. This is one model, this is one of my models. Because the important thing are these black dots. This is data. And the problem is we don't really have much data at very high pressures. So you can imagine this is 135 gigapascal, which is the pressure that we get at the mantle core boundary at the Earth. But we have actually good data only for like a few 10 of gigapascal, only for the upper mantle. So experiments are lacking to really say which models are really good and which ones are maybe wrong. And what happens next? What we also have is the cooling, so the convection and the heat cooling of the planet, which again is connected to the tectonic mode of the planet, also drives a dynamo. And I have a super fancy simulation over here, which I'm really proud of. But so the important thing is, can somebody, I mean it says it more or less here, but does anybody right know how do we get a dynamo, a magnetic field in a rocky planet? Any ideas? Don't read. Any ideas? Yes?
Well, you get magnetic field from, you're getting your heat from radiation, from radioactive particles breaking up. And since those, you have mainly metals in place in those, deep within the core, they're naturally generating magnetic fields.
The one thing you mentioned that's really important is the core. That's important. You know, that's important. So the major point is, think about magnetic fields again. What do we need? We need charged particles moving. But they can't just randomly move, because if you have a random movement, the problem is you actually dissipate this energy, it goes away. So you need specific kind of movement. And that's what I'm showing over here. This is a picture of the core. So imagine this is the Earth's core. And this is the pure solid core, and this is the liquid core. Now what happens is when a planet is cooling, this solid core is growing. It's getting cooler inside. And when it starts to cool, it will cool by thermal convection once, where you have hot material rising, cold material sinking, and so-called compositional convection, which is enormously important. And what that means is when the core is solidifying, it releases the lighter elements like sulfur or oxygen, silicon, whatever is in there. And this is lighter and starts to go up. This represents the rising of these lighter elements. And this is compositional convection. And this convective energy is being transformed into a magnetic field. So we need, in that case, a core, a liquid, partial liquid core, and we need convection in this core. And the convective heat flow in this core is going to be determined by the mantle. The mantle is telling you how much you let out. If the mantle decides no heat comes out, then based on most models, we won't have real magnetic field. Okay. Now, I'm going to quickly speed up to come to the really interesting stuff. The cooling drives the dynamo, and here's an example on the left side. We see some remnant magnetization on Mars, which makes us believe, this is a picture of Mars data, real data, which makes us believe that there was a magnetic field early on in the Martian history, but it disappeared. And what's really important is, that's what I'm trying to illustrate with the picture to the right, if we have a magnetic field, it tells us something about the structure of a planet. As I said, we need metals that are moving. We need some liquid metals, a liquid core. So we need most of the differentiation if the magnetic field is induced by the planet. Or an example in the case of Europa, a Jovian moon, it can be also induced externally. So it tells us something about the composition. It tells us maybe, oh, there's some brine over there, there's some salty water that is actually where a magnetic field is being induced. So a magnetic field helps us to understand what's inside of a rocky body. And what's really important, that's what I've tried to illustrate with this image over here, it's age appropriate almost. So the important thing about that one is I'm trying to show that the interior processes from mantle convection, core cooling, impact dynamo, plate tectonics, and they impact as well the hydrosphere, the oceans, the atmosphere, and life at the end via those interactions. And right now, I'd like to jump into that and look at the connections between the deep interior and life and what we know about that. Now, I'm going to actually build it up in that way that I'm going to start with magnetic fields. And I would like to start with an article for IF Love Science. I bet you all know what the F stands for. but we're recording this, so I gotta be very proper. It says, without a magnetic field, any life on exoplanets may be doomed. Now the question I have, why?
Radiation.
Sorry?
Radiation.
Radiation. So you're saying that the magnetic field protects us from radiation. What kind of radiation?
Solar wind, gamma rays, you name it.
Okay, so it can help us protecting us from solar wind, as an example, from charged particles. Any other ideas? That's a great point. Anything else?
Actually, is the atmosphere.
Yeah, so the atmosphere is important. So the things that we say is the following. We say magnetic fields protect the atmosphere from being eroded by charged solar wind particles, and the atmosphere protects us from UV radiation and the solar wind. So we need magnetic field to protect the atmosphere from being eroded. However, this is what we will find everywhere, and that's a good argument. It's something that we think about. However, we also have to think about something else, and that's if we look at processes that are actually causing the atmosphere to be eroded, then we see that the ones associated with solar wind particles, so charged particles coming from the sun or any star, are actually, in generally many cases, minor. So there's much other loss processes that lead to atmosphere destruction than that. So it's not maybe a major contribution. And also, I just want to highlight that there's been a lot of debate in the last few years. There's been people have been doing work which show that, and that's what this image actually shows over here, magnetic fields don't just deflect solar wind. Look at this picture. We have some solar wind coming over. Imagine that's a solar wind, like a stream. Well, we partially deflect, but we partially also attract. So we attract, of course, in the north and the southern polar caps. We attract all these particles. So we start them to bundle them very high concentration and allow them very strongly to form ions and plasma in the atmosphere. So some people show that actually it might actually lead to more atmospheric erosion. So what I want to highlight with that is that we are actually not really understood so far clearly if a magnetic field is really clearly helping us from protecting us from solar wind and from atmospheric loss. Another example you can also think of is Venus, which has a very thick matte atmosphere and has absolutely no magnetic field. There might be some explanation why, maybe it happened later, but we see clearly that we didn't really understand that yet. And also, so far there's been actually no real evidence for any correlations between mass extinctions on the Earth and magnetic field reversals. So when a magnetic field reverses its polarity, it has a long phase of no magnetic field. But we don't find in geologic record any evidence that there has been any killing of life. However, there's now groups in China and Japan that are starting to really work on that, and they're hunting this, trying to figure it out. So the next years will teach us a lot. But the major point is we have to bear in mind that we have no proof so far that we really need magnetic fields in any way. We have to be very critical. There might be chances, and it definitely are, but so far it's still rather a myth than really a fact. Now, plate tectonics and volcanism. Now, I guess you expect I'm showing you all the time why, planetary mechanisms are important for life, and then I'm saying, well, then maybe not. But you will see, some of them actually are. And let's go to plate tectonics. I found also this nice article over here which says, without plate tectonics, life on Earth might never have gained a foothold. And one thing we're going to say, all these articles I've just taken out from the web, and the people who really do the science, they maybe disagree with that, but they're, of course, journalists tend to take and make something out of things. Let's not forget that. So those people are doing all great work, but the interpretation can be often a bit different. But does anybody know, can anybody give me a reason why this is correct? Please.
An hypothesis?
This hypothesis, why is that correct?
Of life at deep sea vents?
That's a very good point, yeah. But why does it depend on plate tectonics? As I said, there is volcanism without...
Mostly at spreading centers?
That's right, on the Earth, because that's how we have. But you can also imagine, planet without plate tectonics and just volcanism.
Recycling of other elements.
Exactly, so so food, recycling of nutrients on the surface, that's also often an argument. It's a good argument. Any other arguments? Yes?
CO2 in the atmosphere.
CO2 in the atmosphere. That's a very good one. So let's check out the major points for it. One thing is the nutrient replenishing. So with plate tectonics, we bring new fresh rocks. As we've learned from Paul Volkovsky, the Schnapps one, which is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and many other ones. And that's one of the important points. However, another one, which Mick just mentioned right now, is the so-called Uri cycle or the carbon silicate cycle, something that's been very much used in the last 2 decades, actually 3 decades now, in the habitable zone community. What does that mean? Well, this picture is from the original one of the original articles that phrased that down by Walker et al. 1981, and it shows how actually carbon is being taken out of the atmosphere and being put back to the interior and recycled through volcanoes by plate tectonics. And just to illustrate that image, what happens is we got some rocks on land, mostly wollastonite, which are some kind of calcium-rich silicates, and then we have carbon and carbon dioxide and water. And they actually weather these rocks. They break them into pieces. And what happens in that case is we get calcium ions and bicarbonates, and they go into the ocean with rivers. And what happens is we have an equilibrium state in the ocean getting in where we form actually calcium carbonates, which sink down, make layers, and with plate tectonics, then being subducted back to the interior, they melt, and CO2 rises again. So plate tectonics, in the case of Earth, helps us to bring back CO2 to the atmosphere when it's being taken away constantly. And now the important thing is, that's really important, because imagine a few weeks ago we had Dick Peltier talking about ice ages, and told us clearly that there might be a chance that we might have been in a global ice age. And it's been very cold. Most animals didn't like it very much. And the only way to get out of that was just to have continuous CO2 coming up again. And CO2, obviously with climate change, can heat up the atmosphere. And it was getting warmer. And by everything getting warmer, the ice started to melt. Very simplified. Now, that's one of the major arguments, because plate tectonics is closing this cycle. It's bringing stuff back to the interior. And also, what we said before, plate tectonics helps to cool a planet, and by cooling, it helps to drive a dynamo. These are the major arguments. I always like the howevers. However, as I mentioned already early on, CO2 outgassing happens also without plate tectonics. It happens on different timescales, frequencies. And we have to study carefully what are the different frequencies and periodicities of outgassing. But we don't need plate tectonics on Earth, at least, or on Earth-sized planets. It's a bit different maybe on bigger planets. But generally, we don't really need it for having CO2 outgassing. So this first argument is intuitively okay, but it's not really sound. The same thing is with nutrient recycling. Volcanism is there. It's going to bring nutrients. There's many other methods and mechanisms to do that. The Earth and planets are full of different methods to do things. And on the other hand, what we always forget to say, plate tectonics is not always the good guy. Sometimes also, though, he or she, gender neutral, might also be sometimes a bad cop. Because what plate tectonics also does is it actually takes CO2 away for long times. Because sometimes subduction can bring CO2 to very stable sinks in the interior, where you don't get CO2 easily back to the atmosphere. On the other hand, plate tectonics with continental uplift, which is shown in this picture, when we have plates going down, subducting, we also have a push of fresh material to the surface. So we push actually carbonates up to the surface, where they can stay for tens of millions of years stable, and are not being returned anymore to the atmosphere. And as well, we have the so-called Wilson cycle, where we have actually ocean-based information, which prevents, again, the return of carbon to the atmosphere. So what's important is plate tectonics crucially impacts nutrient recycling and climate, but it is not clear how this really happens. And so there's a strong connection. And if we want to understand life on a planet, we have to understand whether there is plate tectonics or not, because it's tightly linked to it. However, saying that we need plate tectonics for life is, at that stage and where we're at now, unfortunately not possible. Okay. I'm just going to very quickly in this general thing, because I'd like to go to the juicy little snapshots. Volcanism, I think it's very intuitive. Things come out there, it brings again nutrients to the surface, but volcanism can also be globally destructive. As we here at MIT have a whole team working on that, the Siberia team. Example, the Permian flood basalts in China and Siberia, which are about 250 million years ago, which flooded the biggest chunk of nowadays Siberia and Russia and China. They caused a mass extinction most likely, or possibly. And so volcanoes can be destructive and also good in many ways. Okay, now are there any questions right now about the general part where I was telling what's happening inside of planets and some correlations, general correlation between planets and the life and the interior? Yes?
So when do we think plate tectonics kicks in the early history of the Earth?
That's a good question. I think we're going to continue that discussion at the end because it's a longer discussion. And there's at least two people in this room who really would like to talk about that, maybe more. We don't know. We don't know. There is good reason to believe that plate tectonics from a thermodynamic perspective started very early on, like almost immediately after planet formation. But there's also good geologic evidence that maybe it started much later, a few billion years later. And right now we have not resolved that issue yet. It's still an open question. 50 years, 60 years of research were not enough yet. Okay, well let me go and tell you some juicy, interesting parts, which I would like to show you how interiors and life can interact and give you two interesting examples. The first thing I'm going to talk about plate tectonics on the Earth and across the galaxy. And I name it the Terra per Astra Terra, and I'm going to explain what I mean with that in a bit. So to dive into that, I want to just give you a little model and dynamical perspective what we do with plate tectonics. Now, when we try to understand how plate tectonics functions, we have various models we can use. We can use very beautiful and most realistic 2D and 3D full convection models, which are very good to represent local behavior, but are really, really hard to run for a long time. So we can't really mess around with them very much because we need just an enormous amount of computers. And we have 1D models, which are just simplified models, which help us understand and approximate what happens in planetary interiors. I usually use both worlds. One helps me to understand more what happens locally. The other one lets me mess around with the whole universe. And so to give you an example, let's imagine we start with a planet that can have any kind of structure. Maybe like the Earth, have a small core, like 30% of the whole planetary mass, and a mantle, or have no core at all, or have a huge core, like Mercury maybe. And have a different mass, can be very small, can be very large. And now let's look inside this mantle profile we see over here. Let's zoom in. And what we see is we have the core, we have the mantle, and we have heat flowing through it. And radiogenic heat sources inside. Now, what we can do is we can then zoom in again in the upper part, where we have tectonic deformation, where we have plate bending, where we have plate tectonics actually happening, where we have deformation occurring. And we can look at many things, and we do all look at many things. Here I want to just illustrate one of these things, because it's the easiest to show you how things can be different on different planets. And in that case, we can just look at actually compare two stresses happening over there. Stresses means forces, more or less. So we're looking at a driving stress, tau d, which tells me how plates are being driven, how something is pulling. So the convective flow in the planet is pulling plates to go down, to bend. And we have a yielding stress, which tells me, tries to prevent this from happening. It's the resistive stress. That's one way of looking at it, a very, very simplified way, but helpful to illustrate things. Now when we do that, we can zoom in there and say, okay, well let's look just at a planet of a given mass m, any time in its dynamical evolution, maybe at the beginning, maybe when it's really old. Age matters in many ways. You'll see actually for the planets many times being older is better, much better. Initial conditions, if the planet started really hot or cold, its evolution, its composition, its structure, everything we can put in. And then let's just simply look how those driving forces divided by the resistive forces change with time. And if they're always larger than one. So do we have always more driving than resisting? That would be one necessary, though clearly not sufficient criterion for plate tectonics. So we have driving. And then we can just look how this function, which I very specifically call x, it's So X is always good for something that is just we have no clue about. How this one changes with time and composition and structure and everything else. And by doing so, it's going to be the only formula I'm going to have. Promise. Trying to keep it to the principles. And just looking, so this function that we want to look at, that has to be always larger than 1. How does it change if I change some material property? That's what this formula actually says. So if I change a property, is it going to be different? Is it going to be, in that case, what's going to be a change happening occurring? It's going to be a good change or a bad change. Now, to illustrate that, I'm showing here an example. I call this property the propensity. It tells you more or less if you change something in a planet, it can be like the water content or the surface condition or whatever, is it good or is it bad for plate tectonics? That means, does it increase the vigor of plate tectonics or not? Does it increase subduction and continental uplift or not? And to give an example over here, this is time in billions of years. And what we see over here is the blue curve is this propensity. And what I've done is I've taken a planet, like Earth-sized planet, and I've changed rock with gummy bears. And actually that happens, interestingly. And what we see is early in time, the value is larger than 0 because I'm plotting here the logarithm, the decimal logarithm. So everything that's larger than 0 means it's good for plate tectonics. The change is good for plate tectonics. Everything is smaller than 0 means it's bad for plate tectonics, the change that happened. So early on, it looks it's better for plate tectonics. So gummy bear planets can drive much more plate tectonics. And like something like 6 billion years, suddenly those gummy bear planets are much worse than a planet that has just rock. And that's all. That's all in here. What I want you to take out of that, the important thing is that this whole thing we see over here is time dependent. So the driving of plate tectonics is not something that is just planet given. It depends on time. It changes. It's dynamical. And now what we can do, we can go back to our models and see what is the most realistic scenario. Hello, Danielle. Oh, sorry, I'm not going crazy. There's just Skype over here. We have a little Skype meeting as well. So the major point is we can look what are the most realistic parameters to drive our models. And there's a lot of uncertainties, which are very important. But we can still right now grasp and have an idea, well, this is the most realistic scenario. And then we can go back, put this in a model again. And then we can start to answer questions. And that's why I say the Terra Astra, from the Earth to the stars. We can start asking questions. What if we know nothing about a planet? And just start saying, okay, let's vary some properties and see how plate tectonics reacts to it. As an example, we can vary the surface temperature. We can vary the mass of the planets. We can also vary the radiogenic heat content in the planet. We can vary many properties. And what we see is, here I'm illustrating, if we increase a property, is it going to be good or bad for plate tectonics? As an example, over here, if I increase the surface temperature, it's going to be bad for plate tectonics. Or if I increase, example, planet mass, it's generally bad, generally red, but sometimes it's good. This sometimes shows you things are not so simple. It depends often on the real evolutionary path of the planet. So, yes?
Could you say what you mean by bad and good?
So what I mean with that is, it's a very unprofessional description for it. It means the driving of plate tectonics, the vigor of plate tectonics is enhanced, which means in that case you can translate it to you have higher subduction rates, you have simply a more active plate tectonic regime. So that means in that case my propensity is larger, which means simply if I make the change, you will have much more vigorous, as I said, subduction or continental uplift. These parameters will scale with that property. That's the major point. That's when good and bad. It's not really a professional term for it. It means it's helpful to increase the vigor of plate tectonics. You can imagine if it's much lower, going to 0, example, there will be no plate tectonics. So this helps us understand if we know nothing about a planet, and for most planets we look out there, that goes back to your question you began to make. We don't know what their composition is like. There might be planets which have much more iron, different cores. Some planets might be maybe undifferentiated. Some planets might even, yet now very, very theoretically and purely hypothetically, have also maybe more carbon. So instead of silicon oxides, we're going to have maybe some kind of carbon-rich planets, which is really hypothetical right now because we haven't found any evidence for that. But they could be alien, and we have to be ready. But this helps us to understand which kind of changes are good or bad for plate tectonics. in a sense I defined it before, good and bad. And this allows us to do this really cool like animation, which tells us, so we know now which kind of properties of a planet can be good for plate tectonics. So we know if the planet has them, its chance of having plate tectonics is bigger than if it didn't have that. And this allows us and helps us to then start making a connection, as I call it, to the stars. In a sense, the formation environment where a planet is forming is not a one-to-one direct connection to the planet composition. However, planets evolving different epochs in the universe, planets that form very early after the Big Bang, planets that form later after the Big Bang, have, on a statistical sense, different properties. Which means, as an example, the ISM, so the interstellar medium, early on has been most likely much more enriched in radiogenic substances. It's been depleted in iron. So we have a track of how iron to oxygen, iron to silicon, iron to radiogenic heat sources change with time. This allows us then to say, okay, like example, what we see here is that very early after the Big Bang, there might have been actually an issue because we had too many radiogenic heat sources, which were not really helpful for initiating and maintaining plate tectonics. So without going into much detail, I'm happy to give you more detail later on, but we start to make a connection to what's happening out there. And this thing I showed before, which is applicable to any planet in the galaxy, we can also focus that on an Earth-like planet. So we can say, oh, let's not go so alien. Let's take a planet which is maybe has the composition of the Earth. And then we know we have much more concrete things, much more thing of the uncertain go into a red or green domain, but it's still uncertain things. But it helps us understand how things have been impacted by different properties. And here, I want to just mention, this is a very scary figure, but I'm going to explain it in detail. And I'm going to just focus on one part of the figure. This is a plot of this propensity I've set for an one Earth mass planet. And what I show here, this is again time, 13 billion years of evolution. I just say, okay, I take a one Earth mass planet, and I have absolutely no clue about its composition. It could be anything, let's say that. And then I say like, okay, I want to just see if I change the composition or the structure or the initial conditions, whatever, in relation to what I know from the Earth, is that planet going to be better off having plate tectonics or worse? So that means this green line here is the Earth. It's always, because I relate everything to the Earth. Or maybe let's have a look at this blue line over here. That's another planet. It's initially a bit better, but then it's worse. So, yes?
I just want to be sure I understand what you mean by better and worse again. You mean more vigorous?
More vigorous, more likely to have plate tectonics.
Or less vigorous?
Yes, so it's more likely or less likely to have plate tectonics. That's the major point. So it's just telling you, if you make a change, is it more or less likely to then have plate tectonics? So if you relate everything to the Earth, this example here, you can say if it's more likely or less likely than for the Earth. And what I want to show you over here, this is showing the parameter space, different evolutionary paths of about 100,000 different planetary compositions and structures and anything. But what I want to highlight is this zone over here. This zone over here. So this zone contains about more like 10,000 different simulations with different composition and different structure, but a kind of like Earth-like composition. So it's dominated by silicate rocks as we know from the Earth. So some planets might, evolve like this, some might evolve like this. But what's interesting is, if you look at this whole bulk, the Earth is this one. That means everything above here, every planet that is representative with an evolutionary path above here is more likely to have plate tectonics than the Earth. Everything below here is less likely at each time step. And what you want to show over here, this yellow zone, as far as we know now, is the most realistic representation of planets out there in our galaxy. That's what we know nowadays. The other domains are hypothetical yet. Possible but hypothetical. This is the most realistic one. And what we see over here, and what I find really interesting and a bit scary, is that if you change many Earth properties, like you change a bit the composition, change a bit the structure, most planets are statistically worse off for plate tectonics. They are less likely to have plate tectonics, which raises the question whether Earth is really close to actually a good configuration, which I always find very scary, because that's something I just don't like when Earth is good in something. But it looks like in that case that actually Earth has a quite good configuration for plate tectonics. Yes?
What is the actual fraction? Because the plot doesn't really show fraction. The area is
Yes. The fraction of the compositions is about altogether 5%, which is above it. So it's not I'm not showing over here. So it's a very small part, that's the whole thing. The biggest fraction is actually worse. Okay, I hope I'm not confusing too much. Yes?
So I understand you're saying that the conditions are different, but are all these planets forming similarly to how Earth formed?
Yes, so those planets have, let's say, they have a similar composition like the Earth. So they have silicates, you know. Imagine it's like a solar system, you know. We have all the planets, all the rocky planets in our solar system, like Mars, Mercury, or the Earth, have similar composition in the sense of they're not crazy alien-like. They have just silicates, you know. They have silicon oxides, magnesium. That's it. They don't have any titanium or maybe carbon or some crazy stuff that we, you know, don't have in a solar system. That means Earth-like in that way. So it means, like, if you look at our solar system, actually, you know, changing the composition, like changing radiogenic heat sources or the concentration of iron or magnesium, it doesn't really many times help to have plate tectonics going. Okay, now back home. So we see now one thing, how different compositions impact plate tectonics in the sense of that they actually create the plate tectonics more likely or less likely when we change something. That brings us back to home and to the question, what about water? So one of the properties we can change is water, as an example. And there's something we see often. People say, why is liquid water necessary for plate tectonics? That's something we find everywhere. People say that water is so super important for plate tectonics. Any ideas? Do we need water for plate tectonics? Is it good or bad in a sense? If we have more water in a planet or on a planet, do we have more likely plate tectonics or less likely plate tectonics? Most people say yes. They say, like, yeah, the more water, the better. Water is important. And unfortunately, when you do the models, and I'll actually spare you now with these figures because I'd like to, you know, finish off my talk in some time. But a major point what I want to show here, so don't focus on the figures, going to be a bit too much info, I think. But when we do these calculations, we see actually that water doesn't seem to be so helpful plate tectonics. So it depends on when. So we see when we want to initiate plate tectonics that water doesn't really have much ways of helping to drive plate tectonics, to initiate plate tectonics. And when we look at how plate tectonics can be maintained, so if we start with plate tectonics and want to keep on going, we see that water, again, doesn't really that effectively seem to help at larger scales. There are some ways that water can help to drive plate tectonics, and that's mostly at subduction zones, where water is intruding into the interior and significantly reducing the melting temperature. And only if that's the case, and that's actually work done by Tim Grove here at EAPS, if his melting temperatures are correct, and I believe they are, then this is a way that the water can help to actually drive plate tectonics. But here's just an illustration again showing that something that we believe is maybe not correct if you really do the calculations. Okay, now I still have my 5 minutes, and because I answered a few questions, I even go for 2 more minutes to show you something much more simple. And I hope, now just shake it off, because now it's going to be something that is less with propensities and all this funny things changing in time. It's something that I find personally very interesting, and I hope some people will appreciate in this room. And that's my work on the geodynamic rise of life on Earth and possibly Mars here. What I mean with that is the following. As an example, look at some well-known serpentinization reactions. Serpentinization is a process where rocks, mostly olivines actually, interact with water, and under certain pressure and temperature conditions, mostly temperature conditions, it's important that the temperature is not too high, but also not too low. And what happens is the rock is being transformed into a material called serpentine, a rock called serpentine. There's many serpentines. And what is being released is hydrogen. If there's iron in the rock, we need iron in the rock. So if you have iron-rich rock, we get some water, we get the right temperature and pressure conditions, we can get hydrogen out of it. Now the interesting thing is, those special pressure and temperature conditions, they depend, of course, on the evolution of the planet, on the age of the planet. It depends on, because we start somewhere inside of the planet, and the planet is cooling. So we have to see where can it actually happen. How does it change with time? And we also need porosities. We need water to be able to get there. That also changes with time. And I'm going to show you just a simple result over here where I'm doing here right now just a 1D model where I take a planet. In that case, it's Earth. Take an Earth-sized planet. And I just say like, okay, I include those chemical serpentinization reactions self-consistently because they also release a lot of heat. And then I say, okay, let's go. Let's see, start at the formation of the planet. We have Earth as it is now in the structure. Start on, and let's evolve it until now. That's 4.5 billion years, and then into the future. And let's ask the question, how much hydrogen can you produce, geophysically driven, by serpentinization? And that's a simplified model. It's much more complex, but I just want to show the simplified result here. And what we see is really interesting. We're looking at the global hydrogen production for the Earth. And we have actually almost nothing. And then we have a steep increase the first few 100 million years. Increases steeply, and then it stays somewhere. And then after like 3.5 billion years, it starts to decay. Now this onset time and this decline time critically depend on the planet mass, planet composition, and planet structure. And that's, I find this image super interesting because if you look at early life on the Earth, the formation of early Earth, it's been very simple microbial life, which most likely used the most abundant source of nutrients out there, hydrogen. And now we have this ability that planets can create this hydrogen, and depending on their composition and structure, they start creating it at different times. And imagine that might drive actually in some way the origin and evolution of life on the Earth. However, what's also really interesting is a steep decline. Now imagine that if a hypothetical planet will depend enormously on those microbes that eat this hydrogen. And then suddenly you say, no more food, we go down. This whole planet might collapse. Now on the Earth, we don't know. Most likely those systems are insulated, so it doesn't matter that much because there's somewhere hydrothermal vents. But we don't know. And now I want to just show quickly the Mars example. Now on Mars we found a few years ago some serpentinites. Serpentinites are rocks consisting of serpentines. So there was evidence that there are some processes like that can happen on Mars. And so I did actually a 2D and 3D models trying to see like, okay, let's make some funky videos and see this is not Mars. You can imagine Olympus Mons is right up here. It's a bit dark to see that. This is the Martian map, full Martian map. And what we're going to say is now, let's run this model. And Mars has a different iron concentration than the Earth, much more iron than the Earth. So it's very interesting because it's actually much higher hydrogen production than we would expect for the Earth. And what happens is the following. Have a look at the video. We start early on to produce hydrogen. And we go on. We fill the whole basin. You'll see that we're going to very quickly, after a few 100 million years, have a peak. It's going to stay close for about 1 billion years, and then it's going to fall down. And what this video shows you, unfortunately, I can't show the time because of a conversion from PC to Mac. Very, very difficult. But what the red spots show you where we have the maximum hydrogen production. Now it's stopped. That means nowadays. So we have, this is a very simple model. I intend to make it a bit more interesting because nature is more complex than just simple. However, I want to show you, this is a very simple model, but the really cool thing is the following. Now let's take the simple model and just look at, this is now Mars, the hydrogen production locally today. And by the way, I use data from orbiters which constrain crustal properties, and then I use models to extrapolate what it means for the interior and the upper lithosphere. And here I just highlight the zones where we have maximal hydrogen production. Now, let's look at the overlap with these zones with where we believe nowadays might be hydrated minerals and maybe water. That's what's left, those red zones. And now let's overlap that with the serpentine findings. Here we go. And interestingly, all the hotspots we have found serpentines. And also interestingly, the only one that doesn't fit in there is actually this west drift. But unfortunately, we have no data over here, so I can't do anything with it because it's a quite deep valley, so I can't have really any data on it. So what it shows us, a very simple model, we already see that where we find serpentines, we also predict to have maximum hydrogen production nowadays. And interestingly, some zones, like here, we believe maybe that there's also subsurface water today. And some zones, no, we don't believe there's subsurface water nowadays, maybe there was. But it shows you, even with a simple model, there might be interesting correlations, geodynamically driven habitats on planets, in this case with serpentinization. Kawabonga. So, now just the message in a nutshell, and that's just one slide. I've hopefully, peacefully, and happily bombarded you with nice things, with a lot of inputs, but the major thing that I want you to take away from all this is just a general idea. It's about understanding that planetary interiors, the ones we stand on out there, they're gigantic, they're enormous. Processes inside are on long time scales, but nonetheless, those processes are most of the times non-linear and in a sense can have a huge impact, sudden impacts on everything that happens on the surface. The interior, without understanding the interior, we really cannot fully understand the evolution and the emergence of life on a planet. Because it's the major driver. It's like we live on the skin and all the organs are inside. And still the organs are what keeps actually us alive. And that's something I would like you not to forget and to understand that whenever we think about life, we have to also understand what's happening inside of planets to fully get a picture. And then another thing I just like to give over here, then two things. One thing is, so we've seen that plate tectonics as an example is very time dependent, very sensitive to how everything happened in which order, so to the path, the evolutionary path. However, as I try to explain with this propensity, there are some, let's say kind of like drivers, there are some trends, maybe that's the right expression, which tell us what is better for actually, what helps us to have plate tectonics and what helps us to actually not have plate tectonics. And this can be used to start thinking of geophysics, of plate tectonics in an astrophysical context. So we can start to address where in the galaxy and when were we able to form planets that are supportive of plate tectonics. And our third thing, just like I give to the students here from the class away, don't trust any scientist, especially not me, but don't trust myths. We gotta look for facts, and specifically in the whole habitability discussion, we tend altogether, we look for great things, but we tend to forget that many things we don't really understand, and there became more myths than real facts. So, with these words, I'd like to thank you, and let's hear some more questions.
Questions or comments?
Yes,
Yes,
I have one comment and one question.
Yes?
Okay, the comment is that the role that magnetic field has in the protection of the atmosphere will strongly depend on the mass of the planet. For a small planet, it will be very important to have a magnetic field. So actually, I cannot say that this is a myth. Probably it's a myth for Earth-like or Venus-like planets, but not for small planets like Mars or even for moons.
Because you would say because the thermal escape is anyway large, and in that case, that would be important component. But even for Mars, I mean, look at the ESA observations, which were a few years ago, when they measured now thermal escape rates of Mars, and just general escape rates of Mars. And they were not conclusive if there's really much happening without the magnetic field, in contrast to Earth with magnetic field. No, I agree with you, there's definitely something, but I don't think we really understood the exact processes. And at least I have not been convinced so far, with like, okay, that's it, The
point is that calling it a myth is too strong for me. Okay.
Okay, we can discuss with that. That's fine.
It does, yes.
There's definitely, we should definitely, I would say like that kind of research, definitely to be supported. But I think we just need really a lot of research until I think people are really convinced with it. And that's what I say. And I think until something is not, a very clear scientific argument, it remains, rather a kind of myth than really a solid full-through fact. And I just like to emphasize that because maybe it's a bit harsh, but I'm just saying this because I think, especially our astrobiology community, we have a bit forgotten to really look at the details. That's all. Well, I'll change a myth for you.
And the question is, life is a major geological force on Earth.
Yes.
So I was wondering if you have thought about the role that life itself has in the interior process.
Yeah, actually a lot. I just see, I think already overwhelmed with too many stuff, so I left it out. That's a great point that you say. So, interior processes impact life, but of course, life can be a strong mediator of impacting interior processes. We've heard that last week by Tyler Volk, who spoke very clearly how life can impact actually weathering rates. So the removal of carbon dioxide from the atmosphere. And of course, by impacting weathering rates, life will also impact sedimentation rates, so it will impact crustal properties. And if it impacts crustal properties, it will also impact what is being transported into the interior, in that case with plate tectonics and subduction. So it will impact the rheology, so the flowability of material, and so it will impact again plate tectonics. So there are definitely feedback mechanisms. However, I gotta say, it's until now it's very clear, very difficult to quantify that. We have to do that, and I think it's a really important question. It's just enormously difficult to quantify it, but it's a great question. More questions? Please, you must.
I have one.
Yes.
You made, I think you talked about it in the middle, that you went on quite a long focus on plate tectonics and how plate tectonics depends on the characteristics of the planet.
Yes.
But I kind of wanted to step back again and ask, is plate tectonics an essential planetary characteristic for
life?
I think you talked about that.
Yeah, there's.
But I'd kind of like to revisit that question.
Yeah, I'll say it like this. I do believe in some way, yes, and but it's not for the reason that people generally use. So the general reasons why people use, say plate tectonics is important for life in general, like a planetary property that is important for really having life, is, as we mentioned, the carbon silicate cycle regulation and nutrient recycling. And these are not really strong arguments. However, there's one connection that's quite interesting, and I think that has to do with oxygen regulation. Now, we've heard in the last few talks as well that oxygen has been quite constant in the last about 500, 600 million years. At least we know that. We don't really know what happened before that much, but it's quite intriguing. It's at first quite surprising, because we know photosynthetic life creates oxygen. That's great. But on the largest time we have on Earth, respiration and oxygen production are quite imbalanced. So whatever you produce goes immediately away. So it's a tough question to answer why we really built up oxygen to that high levels of 21%, and why they stayed stable over the last few hundred million years. And now in that whole connection, plate tectonics is an example, because it brings always fresh material to the surface very effectively. It has the capability to quickly remove this oxygen. And so if you have example, a perturbation in the plate tectonic cycle, you have much more volcanic activity. You could very quickly remove the oxygen in a few million years. And that's surprising, because that power and seeing the same time where we don't have any oscillation usually indicates there might be some regulation mechanisms. And actually there are, as slides I'm not showing, there might be a way that, so my models that I do, I see a very strong sensitivity of the vigor of plate tectonics, especially subduction and continental uplift, to the oxygen fugacity. So if I increase the oxygen content, I actually reduce subduction and reduce continental uplift, which can lead to an effect. If I take too much oxygen out with plate tectonics, put it back to the interior, that's going to slow down the removal again. So it allows it to build up again. And that's really preliminary. The question is really timescales, but it's a possibility. And I think that's something to be explored. Yes?
For the next billion years, does your work say anything about the rate at which plate tectonics are occurring on Earth? Will it be faster, slower?
Yeah, that's a great question. I actually spoke there with Adrian Lenardic, who's hiding here in the public right there. He's been working many, many, many years now, and excellent on plate tectonics.
Making me sound old.
Oh, I mean, he's still very young and right there. But, yeah, so that's a good question. So I would say, based on what I've done so far, I would not expect, on the Earth, what we have random configurations, I wouldn't expect plate tectonics to stop for as long as the sun will last. and assuming it's the same, more or less, surface water kind of regime, that might change. That's a problem. And actually, for the Earth, I find it more increasing. The cooling of the planet drives it actually much more. You could, theoretically, if you go over a threshold, you fall down again. You're getting too cold. So, but for the Earth, I feel, what I see from my results right now is that it's going to actually be more vigorous and more effective. We're safe. Yes, Greg?
Do you need plate tectonics to escape from a hard snowballer?
No. Sorry, that was harsh. No, I don't think so. You're in a hard snowball Earth. What do you need? You need you need CO2. Get out. You need volcanism. You need volcanic activity transporting CO2. Now, you're going to get that also on a stagnant lid planet under most circumstances. So you don't really per se need it. However, and then it comes to however, I've been doing a lot of work on those so-called super Earths, so planets that are much more massive than the Earth, but still rocky. And I gotta say, before I start talking about that, we have to be aware, we don't really know what those beasts are like. So we make a lot of assumptions about their interior properties and so on. But what I see is interesting is that, and actually go back quickly to a slide, if that's fine, because it illustrates it really nicely. Let's go back here. What I see on those super Earths is that actually, come back. Wow, you've seen all those slides? Damn. Okay. Let's go back. It's about melt generation. Yes, there we go. So this figure is really helpful for that. I mentioned one thing in the beginning, and that's, I said that we can still have volcanism without plate tectonics, but of course we need to have form melt. But some situations, even if you form melt, you can bring it to the surface. And that's illustrated by this figure over here. So in this zone over here, where we have higher temperatures than the melting temperature, we might form melt. But in some cases, if it's too deep, too high pressures, we can't put it to the surface. And that's a problem. On some of the super Earths, what happens if you increase the mass, you actually, you shift the zone where you can have melt to actually, that you can extract to higher levels. You have it closer to the surface. But, and that's at the end actually a problem because you're not hot enough over there to do that. So on super Earths, I actually observed that it might be a problem. So if you don't have plate tectonics driving volcanism, and volcanic release, you might have actually a problem of volcanism in general. So for some planets, it might be important. Anybody? Yes? Mary? Or you? Sorry, you go.
Do you think that having plate tectonics, which allows more heat to come out, is necessary or perhaps helpful in maintaining a dynamomagnetic field?
Yeah, absolutely. That's something, yeah, I would say yes.
Do you think you can do it without plate tectonics?
Yeah, you can. You can create a planet that can do that.
Feasibly though. Like
Yeah.
Something
Yes. The problem is always about the time scale. So the problem, and that's why we're still really working. I've got to say, one thing to understand is in the whole solid Earth community, we have still a lot to do. We have figured out a lot, and it's great, but still have also things to understand. And I think specifically for stagnant lid planets, many situations it can become problematic because you have more like heating effects early on, which means if you have interior heating, not really cooling, you actually don't really drive, you actually heat up the core. So early on it might be a problem, but later times, if you're building years later, it should be working. So you might have maybe late magnetic field generation. But that's actually an interesting point because magnetic fields are, I think, the best way of connecting observables, for like some say exoplanets, to interior properties.
What about Venus?
Oh, that's a good case. I think, let's say, what do you mean with Venus?
Why does it no longer have a magnetic field if it ever had one to begin with?
That's a good question.
What do you think?
What do I think? Well, there's actually, the major thing I think is going to be connected to the mantle heat flow. So my guess, and it's a guess, really guess right now, is I wouldn't be surprised if actually the Venusian interior is maybe even rich in water, richer than we think. So the surface maybe it might be dry, but maybe the interior has more water bound water than actually the Earth has, which might actually very much reduce the heat flow. And then the stagnant lid as well helps to even further reduce that. So we might really have a kind of like thermal insulation buffering, which reduces the heat flow very, very much. Another possibility as well is a big part of driving a dynamo is compositional convection, so not thermal. And for this you need a lot of impurities, not a lot, but you need impurities in the core. It might be that the composition is simply different. And the other thing as well is, and that's the mystery of Venus, and I think I gotta mention, Venus is one of the coolest planets ever. We all wanna go and stand on Mars, especially Elon Musk, and that's great because we can't really stand long on Venus. But Venus is actually one of the least explored planets in many ways. We believe a lot that we know what happened over there, but we don't, I think. And that might be the key. There might be something happening, there's definitely something happening in the tectonic regime which made a flip. And that might have to do with that. And we're still ways far away to discover that. But I think Venus is, if I would have like a student who wants to work with something, like go for Venus. You're gonna have fun time the next few decades.
Let's have one last question.
Yes?
What about, in talking about snowballers, there's also been, I've seen this discussion about, well, it's not exactly snowball. There's this argument about how far down to the equator that
Yeah.
you can define your models, and they talk more of a slush ball.
Yes.
And I think Paul Fikowski alluded to that.
Yeah, that was Dick who was talking about that.
Yeah, so have you factored that in your modeling, or?
So your question is, if we don't have a full like hard, so we say like hard snowball Earth, the whole Earth is completely frozen versus it's partially frozen.
Yeah.
That has of course an impact. So there's been also people modeling that, seeing, because then you have still kind of like a weathering feedback, because you still can weather, but the question is how much is left. There's an effect, yes. There's a sensitivity effect, because you can, the weathering rate that you're going to extract might be a bit actually enhanced by the interaction between atmosphere and rock directly.
Okay.
Thank you very much.
Thank you.
Thank you.